Before we start chatting about the details for this thing called 802.1q trunking and also another feature called link aggregation, let's bring this conversation home. Let's use this topology, but let's imagine we have a building. So we have a building, and let's say we have a few floors. So here is the foundation or the basement or the ground level floor. And then let's go ahead and put a few levels in here. So we'll call this floor 1, 2, 3, and 4. Let's imagine we want, on each of these floors, we want high-speed networking devices. So here on the ground floor, maybe we have switch 1. And on switch 1, we have connected to it things like a Windows PC, which would be like this device right here, and then maybe PC 10 and PC 20. And based on how we have configured those ports, maybe the Windows PC is in VLAN 10. So I'll put that here in blue. And then for VLAN 20, I'll put that here in yellow, just as a representation. And then on the second floor, let's imagine we have a couple more PCs there, just as a representation of networking devices. So we'll put PC 10B, and then we label these as well as 10A and 20A. For these two devices. And then the second floor, PC 10B and PC 20B, just as a representation of a few devices on the network. And then let's put here, we'll put switch number 2 and connections with Ethernet cables. And for PC 10B, its port is associated with VLAN 10, and PC 20B, its port will be associated with VLAN 20. And if you're just jumping into this set of videos and you have no clue about VLANs, please feel free to check out the previous set where we took a look at the concept of VLANs and what they do. And then on the third floor, let's imagine we have switch 3. And this isn't from an ideal design perspective, but it's just for the concept of how we can have a VLAN extend across multiple switches. So for switch 3, let's imagine we have the server here. So this is server 1 NUG. And for its port, where it's connected to that switch, that's associated with VLAN 30. And then we are also setting up switch 4 for future growth. So let's imagine we have switch 4 right here. And at switch 4, we currently don't have any access ports, meaning we don't have any customers or end devices connecting to that switch yet, but we're going to add some. So in the case, or in the event that we need a specific VLAN, for example, VLAN 10, to exist, the same VLAN, the same layer 2 broadcast domain. And again, think of a broadcast domain like a room where all the devices live inside. So if we want PC 10B, and Windows PC and PC 10A all to be in the same logical room, how do we extend that room between these two switches? And the answer involves two basic components. One is we need some type of cabling. Now that cabling could be fiber cable, or it could be copper cable, or it could even be wireless. But most of the time in a building, especially a high-rise building, it's very likely going to be fiber between them. However, it could be copper as well. So I'm going to draw the interconnections here between these switches with a red cable. And also we have a cable between switch 2 and switch 3, and also between switch 3 and switch 4, and we could also have multiple cables. So over here, this is representing those inter-switch physical connections between the switches. All right, let me clean that up just a little bit. So over here, we have some fault tolerance with multiple cables, and over here, I'm just drawing one for simplicity. And then the switches can forward frames. For example, if this switch 1 and the PC on VLAN 10 here, PC 10A, is trying to talk to PC 10B, it can go ahead, the switch can forward that traffic over the connecting cable up to switch 2, so switch 2 can deliver it. So one of our traffic patterns would be, for example, from PC 10A to PC 10B, and I'll draw that in blue because they're both in VLAN 10. Another example of a traffic pattern, and let me go ahead and put a dark background here so we can actually see it, would be PC 20A over to PC 20B, which are both in VLAN 10. So let me go ahead and draw a line right here representing that VLAN 10 traffic. So if devices down here on VLAN 10 need to send a broadcast or need to communicate with devices up here on switch 2 in the same VLAN, how in the world? In fact, let's use a broadcast for this. Let's imagine that PC 10A has sent a layer 2 broadcast, and that broadcast, as we learned about VLANs in a set of videos ago, a broadcast needs to be sent to all other devices in the same VLAN. So if that broadcast is sent up to switch 2, how does switch 2 know that that broadcast only needs to go to other ports associated with the same VLAN, in this case VLAN 10? How does it know it's for VLAN 10 and maybe not for all the devices in VLAN 20? And the answer is the switches are going to add a little bit of information to that frame of data saying, hey, this is for VLAN 10 or VLAN 20. And one way of thinking about that little tag that's added is thinking of it like a colored t-shirt. In fact, let's use this topology here. Switch 1 here, switch 2 over here, and we have a broadcast or a frame of data that's coming from a PC in VLAN 10 that needs to go over to a device over here in VLAN 10. So what happens with the tagging is this switch right here, it knows that the frame that came in, for example, from the client PC, it knows that the incoming frame was associated with VLAN 10 because it came in on that port. So before it sends it over this link to the other switch, it'll put a little t-shirt on it. So I'm going to go ahead and draw a little t-shirt here. There you go. And it's not just any t-shirt. It's going to be a blue t-shirt. And so it basically puts that clothing, if you will, or that tag on that frame of data before it ships it over. And that way the receiving switch, when it sees that frame, says, oh, blue colored t-shirt. This layer 2 frame is associated with VLAN 10. And let me label that as well. So VLAN 10. And I'm just using blue as a representation. Now let's also imagine that a few moments later, that PC20 sends a frame into the switch. It's a broadcast. It needs to go to all other ports in the same VLAN, which would include over here port 1/2 where PC20B is, or maybe PC20A is just sending a frame of data from itself at 10.20.0.51 over to the IP address of PC20B at 10.20.0.52. So the IP addresses are the layer 3 addresses. But behind the scenes, the switches need to know also, okay, what VLAN is that for? So once again, the sending switch is going to include a t-shirt. And think of it like the switch putting on the t-shirt over that frame of data before shipping it over. So this time, the switch will need to, before it sends that frame out to the other switch, will need to identify its VLAN 20, so it's going to use the t-shirt game again. So I'll draw another little t-shirt here. Except this t-shirt is going to be yellow. Think of it like a yellow jersey. And that way, when the receiving switch sees it, it says, oh, yellow jersey or yellow shirt. So that way, when the receiving switch sees that frame coming in and it has a yellow shirt on it, it says, whoa, yellow. Or more importantly, VLAN 20, it can recognize that, hey, this frame is associated with VLAN 20, and then it can propagate that or forward that in the case of a broadcast to all the other ports associated with VLAN 20. So the sending switch will put that extra information on the frame, whether it's for VLAN 10 or VLAN 20, and then the receiving switch will simply remove that after it identifies which VLAN it's for, and then continue forwarding the traffic. Now, instead of using t-shirts, what we actually use is a little tag. And that little tag, the protocol for setting up that tag is known as 802.1q. That's the name of the standard for the actual tagging of the frames. And the concept of being able to send traffic for multiple different networks over the same Ethernet network, that is a concept known as trunking. So if we're using 802.1q as the mechanism for the tagging, and the concept of actually sending multiple traffic over the network is called trunking, that's why we refer to it as 802.1q trunking. And if we had 20 or 30 different VLANs, think of it like 20 or 30 different colors of t-shirts that would be injected or added to the frames as they're being sent. The receiving switch would say, thank you, and it's mine, very likely, and then remove the t-shirt and then continue forwarding based on where that traffic in those frames needed to go. Now, there is one case where if we have a trunk set up between two switches, that it won't bother adding a t-shirt. It won't bother adding an 802.1q tag, and that's for something called the native VLAN. And the native VLAN by default is the default VLAN, which is number 1. So to help reinforce that, let's go ahead and take another port. Let's take port, how about 2/2? That's not being used. And on port 2/2, we have a PC or an end device. And let's imagine that port 2/2 here is associated with VLAN 1, which on the trunk, by default, is the native VLAN. If this PC sends a broadcast, and that broadcast needs to be sent over to the other switches, if it happens to be associated with the native VLAN, in this case VLAN 1, where that frame came from, the switch for the native VLAN does no tagging. Sometimes that's referred to as an untagged frame. So if a frame of data is received at the switch, over here at switch 2, and it doesn't have a t-shirt, there's no 802.1q tag there at all, the receiving side will assume, hey, this frame of data is associated with VLAN 1. That's also presuming that both switches are using VLAN 1 as the native default VLAN, which they would be by default. So in short, our custom VLANs are going to have a tag associated with those frames as they go from one switch to the other, and frames for the native VLAN, in this case VLAN 1, would simply be sent without being given a tag. And in this overview, as we're taking a look at 802.1q trunking, I'd also like to introduce you to a potential problem, and that's this. At layer 2, and all these switch connections here are layer 2 connections, meaning they're forwarding frames based on layer 2 addresses. And in the case of trunking, they're adding the tags to let the receiving switch know which VLANs those frames belong to. Behind the scenes, on commercial switches, there's something called STP, which stands for Spanning Tree Protocol. And we're going to have a whole separate video set regarding STP, but the bottom line is that STP is there to avoid loops. For IP packets at layer 3, there is a TTL, a time to live counter, and every time it goes through a router, a packet does, the TTL is decremented, and if the TTL ever gets near 0, the router says, oh, this packet can no longer be routed, and it'll inform the sender. So that's at layer 3 where we have the TTL. However, at layer 2, with layer 2 frames, there's no such thing as a TTL. So if we have two connections right here, and these two trunks going back and forth between switch 3 and switch 4, if there's a packet that's sent here, for example, and it's received over at switch 4, and switch 4 if it's a broadcast, for example, and sends it back. Then when switch 3 receives it on 1/2, it would send it again, and it'd be received again, and it'd be sent again, and we just have a loop. It's called a layer 2 loop. And in a layer 2 loop situation, the network just feels like it's broken. There's hardly any real data traffic that gets through because the frames are just looping at super high speed, as well as consuming a lot of resources on the switch. So spanning tree is there to identify parallel paths like this path here, path 1 and path 2, and it actually disables a loop by blocking on one or more interfaces, so we won't have a loop. Again, we'll take a much closer look at spanning tree in a separate set of videos. But the reason I bring it up here is that what if we took these two physical connections and logically, through some protocols, we made it look like one logical, bigger interface? So in that case, if we see just one big interface, spanning tree won't start disabling a port, and we get more throughput. And the technique to take two or more physical interfaces and make them look like logically one is referred to as link aggregation. And the acronym for that is LAG. So think of link aggregation like taking two or more physical connections between devices at layer 2 and logically combining them on both sides to effectively trick the network into thinking it's just one bigger pipe. So if these are both 1 gigabit links, which they are, the actual aggregate throughput of both of them put together would be 2 gigs in each direction. And that's because in switching, layer 2 switching, we have something called full duplex. And what full duplex means on a single interface is that we have 8 wires, and that's part of unshielded twisted pair if we're using copper here. And those 8 wires go into 4 pairs. And in full duplex, we can use one of those pairs for sending and a different pair for receiving. So we can send and receive at the same time, and that's what's referred to as full duplex. So the takeaway is that we have 2 full duplex connections between a couple switches here, and spanning tree in its default configuration is going to disable one of those 2 ports. We're not getting the full use of all of our bandwidth. So by taking our physical links and making them into a bundle using link aggregation, making a link aggregation group, that can help provide us more throughput, and link aggregation on its own can help prevent a layer 2 loop inside of the link aggregation. So that's quite a bit to chew on in the overview. I get it. So let's do this. In the next video, let's go ahead and break down each of these concepts one at a time. And then once we do that, we'll also start to do the implementation and verification of these technologies so you can get a firsthand view of what they are, how they work, and increase your comfort level and your skill regarding these protocols and these technologies surrounding the world of layer 2 switching. Hey, thanks for watching, and subscribe right here to get the latest information from CBT Nuggets. And if you're new to or considering a career in the world of IT, head on over to CBT Nuggets and sign up for a free trial.